So this is number 51. Place the following substance in an order of increasing volatility. And then we're given a big long list right here. And the number one thing you want to do is sketch the Lewis dot structure for each one of these. And you want to find out what kind of forces hold those together. And so here I've sketched each one of them, just generally. I know I missed some electrons on them, but I just want to know the shape. And then secondly, I want to know what kind of forces hold them together. And so since this one is completely symmetrical, the only thing we have is London dispersion forces, and that's governed by the number of electrons in the structure, analogous to the molar mass of it. Then this guy right here, perfectly symmetrical again, so London dispersion forces, but notice he's got a massive number of electrons, 146. This guy right here may be a little bit polar this way, but only 42 electrons, so London dispersion forces and a little bit of dipole-dipole. This guy may be a little bit of polar this way, but London dispersion forces and a little bit of dipole-dipole. But notice he doesn't have very many electrons. This one's got a lot of electrons again because he's got 3 bromines, and he's going to be a little bit polar because we've got 3 bromines here, and it is asymmetrical, so a little bit of that. Same thing with this one, London dispersion forces, and maybe a little bit polar because we've got 2 bromines over here. So it's going to be kind of like this one, a little bit of a dipole moment going this way. So increasing volatility, our most volatile species would be the one that changes from liquid to gas the fastest, and that would be the one with the weakest intermolecular forces. And so our weakest intermolecular force would be this guy right here, because it has hardly any electrons and only a few London dispersion forces. And so we'll put that way over here, and we'll say that would definitely have the greatest volatility. Then our next strongest holder together here would be one that has the least electrons, because you've got London dispersion forces and dipole-dipoles in all of these, and so it's based on how strong the London dispersion forces are for all of these. So that would be our CH3Cl. And then our next strongest would be the one with the next number of electrons, so that would be our CH2Cl. Our next strongest would be the next number of electrons, so CH2Br2. And then this guy right here, CHBr3, and then our strongest holder together would be our massive number of electron holder right here, CBr4 right here. Now on letter B it says, how do the boiling points vary throughout the series? Well, the boiling point would be the one that sticks together the best and doesn't want to go into the gaseous phase. They would have the lowest boiling point. And so our lowest boiling point would be this guy. Our next lowest boiling point would be this. Our next lowest, our next lowest, our next lowest, and our lowest boiling point, because this would love to be a gas because it has very low London dispersion forces. So it would just go the opposite direction for boiling points, lowest to highest boiling point. And I think I kind of explained it in terms of intermolecular forces, that these guys have the weakest intermolecular forces, so therefore would have the lowest boiling point. These guys have the strongest, therefore would have the highest boiling point. And the other pieces in between are governed by number of electrons, because that decides the number of, or the type of London dispersion forces it has, or the strength of the London dispersion forces it has.